SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, astronomers discover a giant galaxy composed almost entirely of dark matter. A new study to explain why the universe is symmetrical while time appears to be asymmetrical. And SETI detect a mystery signal. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have detected a galaxy composed almost entirely of dark matter, a mysterious substance which can't be seen and which can only be detected by its gravitational influence on surrounding space. A report in the astrophysical journal Letters claims the galaxy Dragonfly 44 is about 70,000 light-years wide and has about the same mass as our own galaxy, the Milky Way, but with far fewer stars and with some 99.99% of its mass composed of dark matter. Dragonfly 44 is located about 333 million light-years away in the Coma Cluster, a large collection of well over 1,000 galaxies. The study's lead author, Peter Van Dokkum from Yale University, says the galaxy has been overlooked until now because of its unusual composition, which gives it the appearance of a diffuse blob with just a few stars. Dokkum and colleagues observed the galaxy using both the 10-metre Keck and 8-metre Gemini North telescopes in Hawaii. Initial observations indicate Dragonfly 44 has so few stars, it should have been ripped apart by its own rotation, unless there was something else holding it together gravitationally. Further observations also revealed a halo of about 90 dense balls of ancient stars known as globular clusters surrounding the galaxy. The astronomy team then used the DEIMOS spectrograph installed on the Keck 2 telescope to measure the velocities of the stars for 33.5 hours over a period of 6 nights. They found the clusters were moving around the galaxy at far greater velocities than would be expected from such a dim galaxy. You see, orbital mechanics tells us that stellar velocities are a good indication of a galaxy's mass. The faster the stars are moving, the more mass the galaxy they're orbiting must have. The observations indicated that Dragonfly 44 must have a huge amount of unseen mass. In fact, the authors estimate that Dragonfly 44 has about 1 trillion times the mass of the Sun. Now, that's similar to the mass of the Milky Way. However, only about 1/100% of all that mass is in the form of stars and other normal matter such as molecular gas clouds. The other 99.99% must be the mysterious substance known as dark matter. Mind you, it's not the first time a galaxy containing so much dark matter has been identified. But what is new is this galaxy's huge mass. The others, which are classified as ultra-faint dwarf galaxies, have similar compositions, but each of those galaxies are roughly 10,000 times less massive than Dragonfly 44. We all know what we mean when we talk about the term time. Wikipedia describes time as the indefinite continued progress of existence and events that occur in apparently irreversible succession from the past through the present and into the future. Time is a component quality of various measurements used to sequence events, to compare the duration of events or the intervals between them, and to quantify the rates of change of qualities in material reality or in conscious experience. Albert Einstein is said to have put it far more simply. Time is what stops everything happening at once. Einstein's special theory of relativity linked time and space into a single cosmic fabric known as spacetime. In fact, time, together with the 3 spatial dimensions, gives us our 4-dimensional universe. But there are a lot of issues regarding time which is, well, just plain difficult to get your head around. Let's take photons, for example. They're the most common particles in the universe. They're also massless and can travel at the speed of light. Consequently, they don't experience time, or for that matter, distance. For a photon, everything is happening at once, and it's happening everywhere. Relativity theory also tells us about time dilation, the fact that time changes depending on how fast you're travelling and how close you are to a given mass. In other words, time for you will slow down the faster you travel compared to an observer. And you age less in the basement than what you would on the top floor of your building, which I guess means your feet are technically younger than the top of your head. So as you can see, time isn't quite as straightforward as what you might think. Associate Professor Joan Vaccaro from Griffith University Centre for Quantum Dynamics has been studying specific aspects of time in order to better understand it in a way conventional physics can't. In the process, Vaccaro has developed a solution for an anomaly of conventional physics which indicate that a mysterious effect called T-violation, that is, violation of time reversal symmetry, could be the origin of time evolution and conservation laws. Her findings, reported in the Royal Society, still result in conventional physics, but also provides an understanding for why the universe advances in time. In other words, why time is asymmetrical. The universe we live in appears to have symmetry. However, when space-time is separated, time becomes asymmetrical. It travels in a preferred direction. The anomaly Vaccaro tries to solve involves two things not accounted for in conventional physical theories: the direction of time and the behaviour of unstable subatomic particles made up of a quark and antiquark known as mesons. In this case, two specific types, known as K and B mesons. Charged mesons decay to form electrons and neutrinos, while uncharged mesons can decay into photons. Interestingly, however, K and B mesons would decay differently if time went in the opposite direction. In fact, experiments show that the behaviour of K and B mesons depends on the direction of time. In particular, if the direction of time was changed, then their behaviour would also change. Conventional physical theories accommodate only one direction of time and only one kind of meson behaviour, making them asymmetrical. But of course the problem is the universe these mesons exist in isn't asymmetrical. It appears to have symmetry. Vaccaro says that means physical theories must be symmetric in time as well. And to be symmetric in time, they would need to accommodate both directions of time and both meson behaviours. And that's the anomaly Dr. Vaccaro is trying to solve. It's a really easy question to ask, but it's a really difficult one to answer. What is time?
Well, yes, you're absolutely right. That is a difficult question to answer. Well, we all deal with it from day to day. We do all kinds of things with time. You know, we proportion it up into bits and we sell our time when we go to work. But trying to understand it is really a difficult question. It's something that's been mulled over for thousands of years. My approach to this is to see how it's different from space. And when you do that, you can make some inroads into the problem. You can get some understanding. If you understand how time is different from space, I think that's the key to it.
We see a lot of symmetry in space when we look at the cosmic microwave background. It sort of looks the same in all directions. There's a bit more of a lump in one area than the other, but there are other things which could explain that. But generally, the universe looks pretty symmetrical. In our every day-to-day existence, we don't comprehend asymmetry in time, unless you're a photon, of course, in which case time is everywhere and everything's happening at once.
Right. That's true. So this is one of the fundamental anomalies in contemporary physics, is that time ought to be symmetric in the same way that space is, but we find this huge asymmetry. And the normal contemporary approach to this is simply to say that, well, we just have to accept it, that we find evidence of a direction of time. These are called the arrows of time, entropy increasing in the direction to the future and so on, and we just have to accept it. And there's a number of things like that about time that we accept as being elementary that we can't question, because, you know, they're part of the fabric of nature. But these are things that I question and trying to understand what time is. So this asymmetry that people are familiar with, the symmetry in time, and that is entropy is increasing. The way that I look at that, I mean, it's a fundamental thing, and we've been studying that for about 150 years now, and we don't know how the universe came to be in such a low entropy state at the beginning, and that's what people are focusing their attention on, to try and understand why the universe had a low entropy state initially. But for me, looking at that entropy doesn't really bring us close to understanding time. Imagine this little story that there's a tree, it's got some leaves and they're starting to fall. This is autumn, and there's a wind blowing, and you see the leaves on one side of the tree, the downwind side of the tree. And if you look at the leaves, you'll say, well, that's evidence of the direction the wind is blowing. But that evidence, those leaves, doesn't make the wind blow. It's just evidence of the direction it's blowing. An entropy increase is like that. So we see an increase in entropy in the one direction of time, and what people have done is linked this increase in entropy so strongly to time evolution that if you see an increase in entropy, you associate time increase, and somehow or other people think that that'll give you the answer to time. But it's more fundamental than that. There's something below it. There's something that is causing time to have this direction, and entropy increase is just evidence of it. So that's what I've done. I've gone looking for something that's below. So that asymmetry that we see, I just see that as evidence, okay, but there's something deeper. And there is another asymmetry that's usually put aside and ignored. And this is to do with another arrow of time called, well, it's called various names. One is matter-antimatter arrow of time, or the elementary particle physics or particle physics arrow of time. And it's to do with a thing called T-violation. It's seen in the decay of certain kinds of particles, subatomic particles called mesons, and there are two types of mesons, the K mesons. Well, there's a number of types, but the two that you see this effect is K mesons and B mesons. And when they decay, you can tell by looking at how they decay that if time was reversed, that they would decay in a different way. The statistics about the decay processes would be different. So this is an asymmetry, a time asymmetry, but it's fundamental. It's not just evidence like the way that entropy is. It's actually a dynamical law. The way these mesons decay, it's due to the weak interaction or the weak force, and that means it's associated with dynamics. So it's a time asymmetric dynamic. For me, that's got to be the key.
One thing Albert Einstein has taught us is that time isn't a constant. It speeds up and slows down depending on mass and speed. How does that play in with T-violation?
That is all in accordance with relativity. So depending on, when you look at the decay processes, the time that they take depends upon the motion of the observer with respect to the particle that's decaying. So time dilation is seen in these processes. You have to actually take that into account when analysing the data. So Einstein's relativity, his space-time background, it's time reversal invariance, so it doesn't make any statements about time T-violation. So in the way that I look at it, what Einstein had done is talked about this space-time background, but the way that objects decay within that background can violate time reversal symmetry called T-violation. It's a background which is in a sense independent from this process. So the thing is, you have this background, the space-time background, and what describes particles decaying is a thing called a Hamiltonian. So the Hamiltonian is this object that describes dynamics, and it's the Hamiltonian that violates this time reversal symmetry. It's not the background. Part of my work has been understanding that that's what makes time different to space, because Hamiltonian, this object, mathematical object, tells us how the universe is translated over time. So the Hamiltonian is a generator of translations over time. So it's really linked with time. To generate translations over space, to move from one position to another, you need the momentum operator. It's a different operator. But the momentum operator doesn't suffer any problems under T-violation or CP violation, these other discrete violations. It's invariant to them. It's only the Hamiltonian that's not invariant to these symmetries or doesn't have these symmetries. So it's only the Hamiltonian that shows T-violation. So what that means is that translations over time will show effects of T-violation or other symmetry violations, but translations over space won't. Now, that has to be a key to understanding the difference between time and space, just understanding how the different translations behave and their symmetries. So that's actually what I put together, looking at these fundamental things, keeping Einstein's special relativity, the space-time background as he defined it, but looking at translation on that background. And that's how I've managed to incorporate quantum mechanics and show that we can have this evolution that comes from this T-violation. This time evolution in my model actually is a result of T-violation. So what I did was I started with a modeled universe in which time and space were treated in the same way. I mean, this satisfies a deep symmetry with me that I'd like to start with something, where time and space are the same. So in order to do that, what I did was I imagined that you could take an object made of matter, and you could place it anywhere you like in space. Okay, well, that's just what we do normally. We can move objects around and they can be at one position and not beside that place and not before it and not after it. They can just be where you put it. Well, I did the same thing with time. So I wanted time to be treated in the same way as space. So I have this model in which I can place an object in time and it will just be at that time. It'll exist only at that time. It doesn't exist before and it doesn't exist after. So I've got a situation where there's no time evolution, where things don't happen. So if you imagine, so this object can be a galaxy, and if you think about it in the way we normally think about it, is that before this particular time, there was no galaxy, suddenly comes into existence and then disappears. And, that violates conservation of matter and conservation of mass and so on, all the conservation laws. And it's a completely weird idea. And there's no way of time evolution because people, if they exist inside this galaxy on a planet somewhere, they would only exist for a flash. They wouldn't have a long life. There's just no time for them. They wouldn't experience time. But in addition to this symmetry between time and space, I also add quantum mechanics and the quantum fuzziness that everyone understands or is familiar with. I add quantum fuzziness to it, which means that when you put something in a particular place, you have to include the possibility that it's jumping around a bit. And that was a tricky bit. But once I put that in, that was fine. I had this model universe, which is quantum mechanical, but it's fixed in both time and space. You can put an object and it won't evolve in time. I add T violation to this, and because it's to do with the Hamiltonian only, it only affects the time dimension. And what happens is that this fuzziness gets stretched out. So the way I describe the fuzziness is a technique used by Richard Feynman, and that is that you have lots of paths. You have a sum over different paths, and these paths are zigzagging forwards and backwards. When I put T violation in, that zigzagging backwards and forwards undergoes interference, and you get destructive interference and constructive interference elsewhere. Only on the time axis. The space axis is unaffected because the way this thing happens. And so it gets ironed out. And what they end up with is the galaxy existing at every period, every moment in time, going into the future and going into the past. So after I've put on T violation, if you ask the question, where would I find this galaxy? Well, it's at any time. If you give me a time, 1 billion years after the Big Bang, the galaxy will be there. 2 billion years, it'll be there as well. Whereas without T violation, you'd only find the galaxy at it wouldn't be a galaxy, but right at the Big Bang, right at the origin. That would be the only place you would find it. So T violation irons out this quantum fuzziness in time that translates objects both forwards and backwards in time, so you find them spread out over time. So we end up with the conservation of mass, because if you find the galaxy at every moment in time, then you have conservation of mass again, conservation of matter. And at the same time this is going on, if you look at the galaxy at different times, in a sequence of times, you'll find it evolving. So now there can be people on planets in this galaxy, and they'll be growing older. So I get both time evolution and the conservation laws. In fact, all the conservation laws, they'll come automatically. And so rather than being elemental, so the conservation of matter is something that we take as elemental. We put it into our equations automatically, and we assume that that's how the universe behaves. And here I find it's not elemental, but it's actually phenomenological, and it's coming from T violation. And T violation is the more fundamental thing. So by being a bit of a maverick and throwing away some, cherished ideas, I've been able to show that those ideas aren't actually fundamental. Well, they don't appear to me, at least. And there's something more fundamental underneath. Yeah, that's how I see time, the difference between time and space.
That's Associate Professor Joan Vicario from Griffith University. Astronomers are trying to determine the cause of a mysterious signal picked up by Russian scientists involved in SETI, the search for extraterrestrial intelligence. The signal was detected by scientists with the Rattan 600 observatory in Russia. Initial reports indicated it appears to have been tracked to a star system known as HD 164595, which is located about 95 light-years away in the constellation Hercules. This star system is already known to have at least one planet, a Neptune-sized world, in a close 40-day orbit around a Sun-like host star. While no one other than the tabloids are suggesting it's ET, the signal is regarded as sufficiently provocative for some scientists to be calling for permanent monitoring of the target system. The signal, detected back in May 2015, is in the 2.7 centimetre microwave band around 11 gigahertz. And the interesting thing is, there are no known astrophysical sources in these super high frequency wavelength bands. However, it's also worth pointing out that this is part of the radio spectrum often normally used by the military. It's therefore possible, dare I say likely, that what the SETI team have in fact picked up is not an alien communication or a new astronomical feature, but rather some sort of, up until now, secret communications burst between military ground stations and their orbiting satellites. Whatever the answer is, we'll keep you informed. NASA's Juno spacecraft has successfully completed its closest approach to the swirling cream and salmon-coloured cloud tops of the solar system's largest planet, Jupiter. Saturday morning's flyby was the closest planned approach during the mission, with the basketball court-sized spacecraft flying just 4,200 kilometres above the Jovian cloud tops at some 208,000 kilometres per hour. There are 35 more close flybys of Jupiter scheduled during its prime mission, which will last until the end of February 2018. Saturday's flyby was the first time Juno had its entire suite of scientific instruments activated and studying the gas giant. Juno achieved Jovian orbit insertion back on July the 4th. Its highly elliptical polar orbit is designed to avoid as much of the intense Jovian radiation as possible. The mission's principal science investigator, Scott Bolton from the Southwest Research Institute in San Antonio, Texas, says all systems were working nominally during the maneuver, which was the first opportunity to take a close-up look at the King of Planets and begin to figure out exactly how Jupiter works. The science data from the past has already been downlinked back to Earth, with researchers now beginning the task of unveiling the giant planet's secrets. Juno's suite of 8 science instruments are designed to help researchers better understand the planet's origin and evolution. Underneath its dense cloud cover, Jupiter is thought to hold the secrets to the fundamental processes and conditions that governed our solar system during its formation 4.6 billion years ago. The spacecraft will look deep into Jupiter's atmosphere to measure its composition, temperature and cloud currents. The probe will determine how much water and ammonia are contained deep within the Jovian atmosphere, which in turn will help to determine which planetary formation hypothesis is correct, or if new ones are needed. Juno will also investigate the planet's gravitational and intense magnetic fields in order to understand its massive Earth-sized core and its mysterious metallic hydrogen mantle. Metallic hydrogen is a substance so exotic, it's almost impossible to produce and study here on Earth. Juno will also map and study Jupiter's magnetosphere near the planet's poles, especially its aurora, Jupiter's northern and southern lights, providing new insights into how the planet's enormous magnetic force field affects its atmosphere. Juno will allow scientists to take a giant leap forward in understanding how the gas giants form and the role these titans play in putting together the rest of the solar system. And as our primary example of a gas giant, Jupiter can also play a critical role to help scientists better understand planetary systems now being discovered around other stars. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com.
For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.
The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
You've been listening to SpaceTime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts, or Audio Boom. This has been another quality podcast production from Bytes.com.
SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, this month exploring the mystery of fast radio bursts.